Hello everybody. For our last section, we're going to talk about the types of volcanoes. So what are we going to be looking at? Cinder cones, composites, otherwise known as stratovolcanoes here, and shield volcanoes. Uh, there are other types. We are not going to get into those. So looking at this in more detail, more than likely you'll get these and you say, okay, well, these look like they are about exactly the same. You have to look at the dimensions on these. So here, I have something about a 1.5 kilometers wide, 0.3 kilometers tall. Notice that it is kind of a parabola shape going up here, as opposed to the composite volcano, a little bit less steep towards the top here and much wider, much taller. Finally, the shield volcanoes are huge in terms of aerial coverage. They are quite tall, but you wouldn't see, like on a topographic map, something that is quite as steep as you would for these. These tend to have gentle, broad slopes. So our first type, cinder cones, these are going to be fairly straightforward. These are built out of little cinders, right? They're blobs of lava, little particles, smaller. You think of like a fist-sized chunk of rock. We put a bunch of those on top of each other to make a hill. You've got your cinder cone volcano. It's a little bit more complicated than that, but not really. Lava tends to be blown violently, but it cools quickly, and the sort of pieces that come down are these rock fragments here. Right? They don't tend to grow too large compared to the surroundings. They're limited in terms of how tall they can really get. You can't stack grains of rice too high is sort of the analogy with this one. And the lava flow event may occur as the eruption is ending. In other words, it's like a shark. You have the eruption first, gas, and then at the end comes the flow. Tend to be scoria and basalt on this one. Are these felsic, intermediate, or mafic? Try to remember. So these tend to be mafic. A couple examples of these. SP Crater here in Arizona. This is up north of Flagstaff. This one is hikeable, believe it or not. I heard it is actually pretty difficult to do this one, but you can actually get there yourself. It requires a tiny bit of going off main roads, but is a nice hike, I'm told. And of course, Sunset Crater. This one you cannot hike in order to preserve it, but this is also a cinder cone volcano. I should see the location of the Sunset Crater, SP up here. And we will talk about this, everything in the San Francisco mountains. These are our composite volcanoes. So these tend to be much taller. These are going to be mountains you've heard of, things like Mount Fuji, everything in the San Francisco mountains in Arizona, things like Mount Rainier. These can grow to considerable heights as opposed to the cinder cones. They can have moderately steep sides and get to be very tall. There are associated hazards with these pyroclastic flows, lahars, which are volcanic mudslides, as well as ash, and they can explode violently, as in the case of Mount St. Helens. And this gives you a little bit of the different parts of it here. Filled central vent. These, the radiating dikes, these are little magma cutting pipes here, which are not the central vent but come off and provide lava to the surface, and pyroclastic layers where this material has built up over time as part of forming a volcano. These tend to be more andesitic, intermediate in terms of composition. Things like Mount Rainier, as mentioned, beautiful, and Mount Fuji. This is what you should be thinking of when you think of a composite volcano. This is the one that should come to mind. Also, these San Francisco peaks in Arizona. And you can actually see here where potentially there would have been an entire mountaintop here that was blown off. Did not necessarily originally look like this. It's also Mount St. Helens, where the top blew off within not too many years ago. And you can actually maybe see it on this one a little bit, sort of a resurging new peak forming in the middle, essentially, a little mound there. So here we have Mount St. Helens in 1980 in its original beauty, and in 1982 after it had erupted and wiped out all this stuff. There you can actually see it really well, the little resurgent mound in the middle as it continues rebuilding. This one is still active, of course. If you want to learn more about these, there are some great videos, articles on them that I've included here. Finally, we have shield volcanoes. So these are larger, in terms of aerial coverage, much larger, broader volcanoes, right? Things that are like this shaped. You imagine, we call them a shield volcano because it's like you're looking at a shield from the side, almost just that broad sort of slope, much wider than it is tall. Uh, and you can actually see the parts of it here, our magma reservoir, our central vent, and the summit caldera, which are going to be considerably less offshoots on these sometimes. A lot of what comes out of these is going to be thin stuff, the runny stuff. It's going to spread out in all directions, so not as conducive for building straight up. Travels a long way, leading to these sort of shallower slopes. Goes up slowly over time with many, many, many eruptions. And because these tend to be basaltic, we would not expect them to explode quite like an intermediate or a rhyolitic volcano would. An example of these, so the Hawaiian Islands are going to be shield volcanoes. These are built up very, very many lava flows on top of each other to make these things, which are not completely just mountains, right, but more like giant shields sticking out of the sea. And you can actually see, especially for Mauna Loa and Mauna Kea, we have to look here. With this one, you can see spectacularly that the next two numbers in the access code are 55. Again, the broad shield sort of shape for this one, same for Mauna Kea. So we have lava flows which run in all directions, basaltic lavas, very, very low viscosity, spreading out and slowly building these. So why do we have all these different sorts of volcanoes? What makes them different from each other? So it's all based on where the magma is formed, right? How deep it is, what it is located next to, and where the magma comes from determines what elements are in it, the chemical composition, the makeup of the magma, which determines the viscosity, which determines how explosive this thing is and the threat to human life. Again, on geology being a useful thing to know, this tells human beings something about how dangerous it might be to build next to a certain volcano. Use your knowledge of geology, you figure out how dangerous it might be, you know where or where not to build buildings. And you might be able to put it together with this one here, thinking about it. So where would you expect the shield volcanoes to be on this? Where would you expect the cinder cones to be? Where would you expect the composite volcanoes to be? Now you have all the information necessary to figure this one out. You might also be able to give a little bit more context to this one here. So which of these three would you associate with which type of volcano necessarily? It may not be a perfect fit, maybe there is, but you should be able to get some sort of idea of how this sort of table here might relate to something that's a little more real, the story of a volcanic eruption. This is giving globally where we have volcanic activity. And you can actually see, well, there's not just volcanoes on this one, but you have hot spots as well. So things that are just in the middle of a plate. What could cause these? And this is one of the questions in geology which, as far as I know, has not been settled, what the origins of these are. Some explanations is that these actually are coming from deep mantle plumes. You have this hot material that comes all the way from the core mantle boundary and rises up and gives us the lovely Hawaiian Islands over here, for example. Or Yellowstone, which many of you, I'm sure, have been waiting for. That one is a hotspot volcano. It is not related to a plate boundary, but it is due to some inside of the plate sort of mechanism that would drive it. These are generally less well understood, and of course we should all hope that this is not something that we ever need to really understand in many, many lifetimes. We'll let people much later prepare and deal with that. This is Arizona. So we have the distribution of volcanics through about 200 million years. All the recent stuff is in Flagstaff. It's all going to be up here in the Flagstaff area. You can also see a little bit of our median age, 5 to 16 down here, surrounding it and getting a little bit older as we move away from Flagstaff. A little bit of new volcanic activity over here in Springville. So, if we look back at this, which parts of this have we covered? Well, in this unit we have covered everything here, volcanoes, extrusive igneous rocks, as well as what's going on here, magma and the crystallization process, and a little bit about the melting. Okay, what are our big ideas for the unit? Well, first you should know that the next two numbers in the access code are 9-1. Next, magma and lava. What are the difference, not just in the definition, but in terms of meaning? What is the explanation that might be different about these? What about the rocks that come from one or the other? Where do magmas come from? Going all the way back. You see a volcano. What is the origin of this stuff that is coming out of it? Where did it come from? How did it get to be there? What is the process in between? Igneous rock textures. So what does this mean here? Venerate. What is vesicular? What is the basis of telling these rock textures apart? Extrusive hazards, right? What is dangerous? What isn't? What makes different things dangerous? What sorts of volcanoes are associated with certain hazards? There's been a lot on this. And finally, types of volcanoes and some examples of these, including the ones in Arizona. That's all. Thank you.